Swayam Prabha. Digital India. Educated India.
So we will continue our discussion on network flows, bipartite matchings and some related things in this class. And in fact you have already seen this inequality, that is for bipartite graphs. You know that the size of the maximum matching, this size is exactly equal to, minimum vertex cover, MVC, right. So the size of the minimum vertex cover and the size of the maximum matching are exactly equal in the bipartite graph. To recall what is a vertex cover, so in any general graph one can define a vertex cover, and a vertex cover is a set of vertices. So for a graph G equal to VE, a vertex cover X is a subset of the vertex set such that for every edge UV belonging to E, what property should hold? At least one of U or V or both must belong to the set X. In that case you will call X as a vertex cover of the graph, right. And when we say that if it is a minimum vertex cover, it is a set of vertices which has the smallest size amongst all such subsets which satisfy this property, right. So in this graph we have a vertex cover which can be this vertex, and let us say this vertex. Is this a vertex cover? Does it take care of all edges? So it certainly takes care of this edge, it takes care of this edge here. So it does take care of all edges. Can you have a vertex cover of smaller size than this? So one needs an argument, but you can argue that in this graph you cannot have a vertex cover of size smaller than 3, right. So let us look at a particular example and note that the size of the maximum matching and the size of the minimum vertex cover need not be the same always. You may have seen this earlier. So this graph, which is simply an odd cycle, will have a maximum matching. So I will denote matched edges by, let us say, this. You cannot have a matching of size more than 2, that is clear, because you have an odd number of vertices which is 5, and the maximum matching is upper bounded by n over 2 seal, which is here 2, right. So therefore you have a maximum matching of size 2, and again you cannot have a vertex cover of size 2 here because you must take in 3 vertices at least. So a particular vertex cover could be this, right, and it is easy to argue in this case that this is the minimum vertex cover, and therefore the maximum matching size need not be equal to the minimum vertex cover size in general graphs. What we want to show is that this is true in bipartite graphs. So I will just make a small detour and ask, so what we are saying is, if G is bipartite, then this condition holds, right, that is maximum matching size is equal to minimum vertex cover. So in terms of our necessary and sufficient conditions, remember we saw them in the context of Hamiltonian graphs. Is this a necessary condition or a sufficient condition? It is a necessary condition, right, it is a necessary condition. So if G is bipartite, then maximum matching is equal to minimum vertex cover. Let us ask, is this sufficient also? That is, if the graph has the property that maximum matching is equal to minimum vertex cover, then the graph is bipartite. This is not the purpose of our lecture here, but just a small fun question that I would like to ask. Can you think of non-bipartite graphs which will also satisfy this property? This is a non-bipartite graph which does not satisfy the property, right. So in fact let us look at this graph, which is non-bipartite for sure because I have already added an odd cycle, and let me add one more edge to it. So now what is the size of the maximum matching? The size of the maximum matching is 2. The size of the minimum vertex cover is also 2, right, because I simply need to pick 2 vertices from the odd cycle, and then I will be able to cover all the edges. So in fact this condition is not sufficient for a graph to be bipartite. On the other hand, the condition of no odd cycles is necessary and sufficient. I just wanted to bring out this distinction. In literature, these graphs are also called as KEG graphs or Koenig-Egervary graphs, because they satisfy this condition of maximum matching size is equal to minimum vertex cover, but they are not necessarily bipartite graphs. So Koenig-Egervary graphs are a larger class of bipartite graphs. Right? So this is just for your information. So what we want to prove is Koenig's theorem. So maybe I should say reprove, because you have seen a proof of the Koenig's theorem. We are going to prove it using different techniques, and I want to emphasize this graph theory and graph algorithms are very intertwined. I mean, you should not treat them as two different things. In fact, one may be useful at other places, and so you will see now that techniques in network flows are going to be useful to prove several things. For example, you can get a proof of Menger's theorem, you can get this Koenig's theorem, and this is one of the things that we will illustrate here. So what does Koenig's theorem state? It's exactly this: if G is bipartite, then the maximum matching size is equal to minimum vertex cover. Right? So what we will do algorithmically now is that we have already computed a maximum matching by saying that I will take my bipartite graph, convert it into a network flow problem and ask for a maximum flow. We have already seen a algorithm for the maximum flow. Therefore, we have the collection of edges. In fact, we have the flow network, we have the residual flow network corresponding to that. All of that we are going to use to actually construct a vertex cover which will have the same size as the size of the maximum matching, and we will argue that indeed these two sets have the same size and the set that we have constructed is indeed a vertex cover for the graph. So that is the goal of this lecture. So let us recall the reduction to the maximum matching problem. We had in fact introduced this vertex S and a dummy vertex T and added the edges accordingly. So let me say that in this bipartite graph, so I am purposefully not drawing the directions of the edges, but let me say that A1, B1 and A2, B2 belong to the matching. So I will also draw them matched. So A1, B1 and A2, B2 belong to the matching. Now, is this a maximum matching? So if you want to show that this is not a maximum matching, you should simply give me a larger matching. That will convince me that this is not a maximum matching. And you can try to apply your augmenting path theory that you have learned to see whether there is an augmenting path. It is a maximum matching, right? So now we would like to show that this is a maximum matching. In the course we will also show a vertex cover of the same size and also prove that there is no augmenting path, right? So by our theory that we had seen earlier, if this is the maximum matching in the corresponding flow network, what should be the value of the flow? We will believe him that it is a maximum matching. So what would be the value of the flow? 2 units, right? So let us draw the residual network corresponding to that flow, which is of 2 units and from which we must have constructed this maximum matching, right? So how will that flow network look like? So please help me draw that flow network. So S and T are there. What should I draw? Let's fix the edges from S to the A side, or okay, X side, but I have called these vertices as A1, A2, A3. Yeah, so what are the edges from S to? It will be because if you have chosen A1, B1 in the matching, you must have sent 1 unit of flow along that edge A1, B1 which was directed like this. Therefore, in the residual network, remember we are constructing the residual graph directly. I am skipping one step, but this edge itself is reversed and therefore this edge must have also been reversed. Similarly, this edge is also reversed. All of you agree, right? So in the same context, I will also draw these edges which are reversed. What about the rest of the edges? sorry, this is reversed edge. What about the rest of the edges? They are all forward, that is A3 to B1 is a forward edge, A2 to B3 is a forward edge, similarly S to A3 is a forward edge, and this is a forward edge. So this is how the residual network looks like with respect to the maximum matching or the max flow, corresponding max flow. So let us, so for the max flow min cut theorem, we had built a set S in the residual network, right, the set capital S. And what was that set, if you recall? All vertices which were reachable from S in the residual network. So in this residual network, which is GF, so let us pick up all those vertices. So what are vertices which are reachable from S? Clearly little s always remains reachable, yeah, A3, B1. What about A1? So A3, B1, A1 is also reachable, right? Anything else? There is also one more nice thing. So all these vertices are reachable. So B3 reaches T, therefore A2 reaches T, therefore B2 reaches T, and you cannot possibly have something any of these reachable from S, otherwise there would have been a ST path, but you must have stopped because there is no ST path in the residual network, right. So this is a clean graph in which you can argue this way, and but anyway we have constructed this set S, right. So okay, so what we want to show is the conics theorem, and what we want to argue is that we can pick up exactly two vertices in this graph or maximum matching many vertices in this graph such that they form the vertex cover, right. So if I give you a maximum matching, it clearly tells us that from every matched edge you must pick exactly one endpoint. Which endpoint we do not know, right, and we are going to give a method for this, right. So before we give a method for this, let us observe something about this set S and its relation to this XY bipartition that we have. So one is, observe that the set S that we have constructed need not only contain vertices from one side of the bipartition. As we have seen here, it contains A3, A1, it also contains B1. So in general, if you look at the set capital S, which is reachable from which is the set of vertices reachable from little s in the residual network, they may contain vertices on both sides. So the picture that I will draw in general is that there is a residual network, there is S, and there is a whole set of vertices on the A side and on the B side which belong to the set capital S, right. This is how the picture looks like, just that in this case it is cumbersome to draw it, but this is how the picture looks like, and there are these rest of the vertices. There is no other vertex and T must be here, right. The rest of the vertices, I have not said that all of them reach T, in this case they happen to reach T, okay. So let us observe these sets and make some observations about this. So we will call this part of the graph as S intersection X, this part as S minus X, this part as, this meaning this part as S intersection Y, and this part as S minus Y. Just we will name these are exactly what they are, that is S intersection X is this, S minus X is this, and so on, okay. So remember that this whole flow network and residual network had come from a bipartite graph in which the edges in the internal bipartition which carry unit flow correspond to a maximum matching. So we could also ask, what are the, if there are some vertices on the A side which have on the X side which have been left unmatched by the maximum matching, in which part should they belong to? Will they belong to S intersection X or will they belong to S minus X? So the question is, if there is a vertex which is left unmatched by the maximum matching, then in which part will it belong to? Of course it is in the X side, so it must belong to either S intersection X or S minus X. So S minus X, what is the intuition or what is Why would you say that it belongs to S minus X? Remember what is S? S is the set of vertices that are reachable from little s in the residual network. I am very sorry, so it is X minus S. Yeah, so similarly this is Y minus S. Yeah, okay. So this is this. Thank you for correcting me. So these are the sets. So in which part will it lie? Will it lie in S intersection X or the remaining part? Okay, what is the intuition? So what you are saying is such vertices will not be reachable from little s, right? That is why they have been put into this part. So okay, so let's frame the question correctly. A is a vertex which belongs to the partition X, and the claim is A is unmatched with respect to the maximum matching. Therefore, we are asking where does A belong to? A belongs to S intersection X or A belongs to X minus S. Where does it belong? Why should it belong to S intersection X? Good. So remember that in our original network we have put this edge from S to each A. It is unmatched, so therefore there is no flow going into it, and therefore that edge remains as it is. Just like A3, which is unmatched with respect to the matching, you are seeing that the edge S to A3 remains as it is. Therefore A3 is reachable from S, right? So such vertices, so all unmatched vertices on X side belong to S intersection X. Does everybody agree? Because those vertices are unmatched, they do not get any, they are not carrying any flow, therefore the edge S to that vertex remains intact in the forward direction and those vertices continue to be reachable. We cannot say that only unmatched vertices belong to this, because we have an example. For example, A1 is a vertex which is matched but still belongs to the set S intersection X. So it is not only made up of unmatched vertices on the X side, it can have matched and unmatched vertices, but if a vertex is unmatched, it belongs to the, if a vertex is unmatched and belongs to the X side, it belongs to S intersection X, right? Let us ask the similar question in terms of if a vertex is unmatched on the Y side, where should it belong? You can again take the example as a clue, but you should also argue why it is true in general. That is why we have an example and a picture which is the general picture. So where are unmatched vertices on the Y side? State it again. So your claim is that all unmatched vertices must belong to, all unmatched vertices on the Y side must belong to Y minus S. So all unmatched vertices on Y side must belong to Y minus S. This is the claim, right? Okay, so what is the argument? So if it belongs here, then it must have a path to T, and already all such vertices have a path from S. So therefore you will exhibit an S to T path, right? But that should never happen in a residual network when you have achieved the max flow, right? Therefore you cannot have unmatched vertices on the Y side belonging to this part, that is S intersection Y, right? So what we know is that if there are unmatched vertices on the X side, they belong on the upper part, which is S intersection X. If there are unmatched vertices on the Y side, they belong in the down part, which is Y minus S, right? Good. Now let us ask about matched edges, right? So there are matched edges in the graph. So let us ask if there is a matched edge. So first let us say that there can be matched vertices here, right? And we have seen why there can be matched vertices. For example, there is an unmatched vertex here which was A3. It has a neighbor which is reachable by a forward edge and which is matched here, and this was the matched edge, right? So let us ask, where are the matched edges lying? I mean, the only way they can be sitting is they can be completely contained inside the S part, or they can be completely contained inside the non-S part, that is they are horizontal edges, or they cross this, right? That one endpoint is in S, the other endpoint is not in S. I mean either this way or this way. These are the only ways, because anyway this graph is bipartite, so you cannot have edges inside x completely or y completely, right. So we want to ask whether where do the matched edges lie, correct. Okay, so let us ask if there is, okay, so vertices here are all matched, that is what we claim. So here all vertices are matched, here also all vertices are matched, that is what we said, that is unmatched vertex if it belongs it must lie on this side, unmatched vertex if it belongs. So what we are essentially asking is where does this matched vertex have its partner, right. So what we know is whenever an vertex is matched, its matched edge has been reversed in the residual network, and therefore if this vertex was reachable from S via some path, then using that reverse edge its matched partner is also becoming reachable from S. Therefore its matched partner must also belong to the set X S intersection X. Is this clear? So let me repeat the argument. All the vertices here are matched, that is what we have argued, and we know that if a vertex is matched, it's the edge to which it is matched on the y side, its edge has been reversed in the residual flow network. Therefore if this vertex was reachable from S via some path, then its matched neighbor must be reachable from S via the reverse edge. Clear? So therefore all such vertices, all such matched edge, everybody here has a matched neighbor inside this, in fact all the vertices that are here are matched and they have their matched neighbors sitting into this partition. Now but this does not forbid us from saying that maybe there is a vertex here who also has a matched neighbor here. Why? Sorry, so suppose this was a matched edge, yeah. Okay, so again you use the same thing, right. So these kind of edges. Okay, just okay, T is here actually. Okay, yeah, so the question that I should ask is what about these edges? I mean maybe there are vertices here which are matched, but they can have their partners, the matched partner inside this set which is S intersection X. Can this happen? So these are matched edges. There are some unmatched vertices here that we have agreed. If there are matched vertices here, can they have their matched partner inside this set? So in fact you should ask yourself that if you get a matched vertex here in this part S intersection X, how did you reach that matched vertex? Remember all such vertices must be reachable from S, right. So you must have come to this matched vertex along a matched edge, right, and where do this matched edges belong to? They must have already belonged to this side, right. So therefore there cannot be edges of this form which are matched, because every matched vertex is belonging to this set S intersection X, because its matched neighbor is actually belonging to the set S intersection Y, right. So therefore you cannot have vertices which are matched and they have the here in Y minus S and still have their matched partners here. Is this fine? Okay. So what this argues for us is that so then where should these vertices have their matched partners? There can be matched vertices in Y minus S also, right. So where can they have their matched partners? They must have it in X minus S, right. So therefore all the matched edges all the matched edges are, we will call them as horizontal, right. They are either belonging completely to the S side or belonging completely to the X minus, I mean not S side, I will just say not S side, right. Okay, good. But there can still be edges of the graph which cross these sets, right. That is, some has one endpoint in S, another endpoint not in S, and so on. So in fact let us see this S side in this example. So here this is the vertex which is belonging to S, this is the vertex which is belonging to S, and there is another which is B1 which is belonging to S, right, and the matched edges are all, so A2 B2 which is belonging to the non-S side and A1 B1 which is belonging to the S side. Again, the example is only a reconfirmation of what we have argued in the abstract sense, but what we are doing it is in the general setting where you have any bipartite graph, and we are keeping this example to validate our claims. Okay, so now what I claim is that, okay, so all the matched edges are sitting horizontally in this picture. So what I will do is I will look at this set which is X minus S and S intersection Y, this part, right? Yeah, so I will look at the vertices which are here and here, that is S intersection S and X minus S and S intersection Y, right. So if I pick up only vertices from here, remember that all the vertices here were matched. We have argued that all the vertices here were matched because we argued that unmatched vertices in the X side must sit on the above part, unmatched vertices on the Y side must sit in the part which is below. So all the vertices on this side are matched, I mean all the vertices in these two sets are matched. So my claim is I will pick up all the vertices in these two sets, and I have certainly not picked up more than maximum matching many vertices, right. So currently we have a maximum matching. All the edges of the maximum matching sit horizontally in our picture, that is they belong either to the S side completely or they belong to the non-S side completely. I took S minus X, the endpoints of the matched edges in X minus S, and I also looked at the matched edges and picked up the S intersection Y endpoints. So these are clearly vertices. I picked them up, and I have certainly picked no more than edges that is the size of the maximum matching. In fact, I have picked exactly equal, because for every edge in the maximum matching I have picked one of its endpoints, but I have picked one of its endpoints cleverly. So now I would like to argue that this set of vertices in fact forms a vertex cover for this graph. If I prove this, then I will be done with the proof that in fact maximum matching is equal to minimum vertex cover, right. So